Hello GCT Chemistry class. In this video we're going to be covering the end of the module 13. It'll be pages 473 to 480. We'll be covering examples 13.6 and 7 and on your own 13.9 to 13.12. So our bridge to the last unit here is the concept of entropy, which is a measure of disorder that exists in a system, and it's abbreviated by this delta S. And in this part of the chapter, we're looking how to quantitate a sense of entropy while looking at chemical reactions. And so there's some guidelines here that the book outlines on how to compare the reactants to the products to determine which side has greater entropy. So, for example, the first principle is to look at the number of molecules and the phase. So we're looking at these letters here that would indicate whether or not it's a solid, a liquid, or a gas. And it can also be considered aqueous, which would be an AQ. That's something that's dissolved in water. So first we say the most molecules in the gas phase has the highest entropy, or the highest S. So in this particular equation, right, we have gas both for the reactants and the products, but since the products has 2 plus 1 molecule on this side, or a total of 3, versus 2 on this side, this has more molecules of gas, so this would have the higher entropy. If there is no gas in the products or reactants, then the side with the most molecules of liquid or aqueous components would have the highest entropy. And if all are solids, then the side with the largest number of molecules has the highest entropy. So let's look at some specific equations and see if we can determine the sign of the delta S. In this equation here, the zinc plus the hydrochloric acid forming zinc chloride plus hydrogen gas. We look at the different phases of matter. We have solid, aqueous, and gas. So, since there's gas and aqueous on this side, which has a higher entropy than a solid and an aqueous, the product side would have a higher level of entropy, and therefore it goes from a state lower to higher, and that's considered a delta S that's positive. In the next equation, we have all of the molecules in the gas stage, so then we start comparing the number of molecules. So we have 1 plus 3 here, right? It's an imaginary 1 before the nitrogen, plus the 3, that's 4 on this side, versus only 2 on this side. So 4 to 2, the 4 is higher, going down to lower. So in this case, the delta S is considered negative. And then finally, in this equation, we have a solid, yielding, and aqueous, and liquid. Well, clearly the aqueous and liquids would have the higher entropy versus solids. So this has a delta S of being positive. So we're going to look at on your own 13.9 on page 474, and we're analyzing a few more reactions just so we can get this down pat. And so we have this reaction, C2H4O2, which is acetic acid, plus the sodium bicarbonate, and we're looking at the different phases. We have aqueous and solid, yielding sodium acetate in the aqueous phase, a liquid, and a gas. So since we have gas over here, we're tipping the scales with the higher entropy in our products. So it goes from low to high, and that's a delta S of that's positive. Here we have the same reaction that I had on the other slide. It's the decomposition of hydrogen peroxide. So we have all gas molecules, but we have 2 on this side and then 2 plus 1 on this side. So this side is higher because it's a total of 3. So going from lower to higher, the S is positive. And then finally on this equation, we have aqueous yielding solid and aqueous. Since we have more aqueous molecules on this side, then it would go from higher to lower, and then in that point the delta S is negative. All right, so we can apply some of the similar mathematical principles that we've been using early in the chapter to quantitate this change of entropy, and we can use it in this equation here, the delta S being the sum of the change of entropy in the products minus the sum of the change of entropy of the reactants. And that should look very familiar to you because our change in our delta H formula was very, very similar. And in this type of calculation, we use a table, just like we did in the other problems, which will help us generate a specific number for this for an equation. And the book just likes to point out these values are all positive because they're actually reporting the value of S and not actually the delta S. So we're going to look at an on your own here, 13.5 on page 475, and I've just repeated the equation here. And there's sort of recounting one of the previous problems. It says in problem 13.5, you determine the delta H of this following reaction. And it says use what you learned to calculate delta S for the same reaction. So again, you'll remember in this, we start with the product side, which is over here on the right. We have the calcium carbonate. We would look that up on the table, and we have 92.9. We realize there's an imaginary 1 here, so it's 1 times the 92.9, the units being joules over moles times Kelvin. And then we subtract the reactants, which would be over here. And we have the calcium oxide, which is here on here. It's 1 times 38.2. And in addition, we would subtract the carbon dioxide, which is on the chart here, the 214, so it's 1 times 214 for a total of negative 159 joules over Kelvin. The moles, you can see, end up being eliminated, and so our units there for the change in entropy is the joules over Kelvin. Okay. So I just want to make mention on these pages of the chapter, which is 475 to 476, the author has a discussion about how the second law of thermodynamics may be interpreted in terms of current theories of evolution. So he makes these comments that the current theories of evolution, and he's talking about biological evolution, are not consistent with the second law of thermodynamics because they would, quote, require each step of evolution to be accompanied by an increase in the entropy of the surroundings. And so I would just encourage you, if you'd like to learn more about his details on that, to read more in detail on those pages. All right, so now we're moving on to this concept of the Gibbs free energy, which here we finally have a symbol that connects to the first letter in that word. And this integrating the information that we get from the values of delta H and delta S. And this equation here, it says that the change in the Gibbs free energy, right, accounts for delta H minus the temperature, which is measured in degrees Kelvin, times the change in S. And so interestingly, as he looks at different chemical reactions, a few principles come up. It says when delta G is less than 0, the reaction is consistent with the second law of thermodynamics and it is spontaneous, versus if the delta G is greater than 0, the reaction cannot proceed because it would violate the second law. And once again, we have another equation that's very similar to our delta H and delta S. We have the sum of the change of the Gibbs free energy formation of the products minus that of the reactants will give you a quantitative value for delta G. And we have this table that can help us fill in some exact values. All right, so let's look at example 13.7. And again, they're referring back to an older example here. It says, in example 13.3, we studied this reaction. It's the formation of nitrogen dioxide by combining nitrogen monoxide with oxygen gas. It says, and it's found that the delta H was negative 114.2 kilojoules if its delta S is negative 147 joules over moles times Kelvin. What is its delta G at 532 Celsius, which they kindly convert to Kelvin here, 805 degrees Kelvin. And we ask, is it a spontaneous reaction at that temperature? So our goal is to work with this formula here to be able to input values into that and solve for delta G. However, we first have to reconcile these two units. We have kilojoules here and joules here. So we're going to convert the joules per mole Kelvin to kilojoules so that these units would be the same. And we simply divide by 1,000 and move the decimal point over 3 times. So we have 0.147 kilojoules over moles times Kelvin. Now that we have that reconciled, we can start plugging in values into this equation. So our delta G equals delta H, so this is given here, negative 114.2 kilojoules per mole. Then we have minus the temperature, was given as 805 Kelvin. And then the delta S was given, and we converted it from joules to kilojoules, so we'd substitute in the 0.147 kilojoules over moles Kelvin, and we get 4 kilojoules over moles. So it asks, is it a spontaneous reaction at that temperature? Well, if you remember back in this other slide that, just trying to find it here, when G is greater than 0, then it's not spontaneous. So in this case, the answer would be that it is not a spontaneous reaction. All right, let's look at the second in this set of examples. It says, is there any temperature at which the above reaction does become spontaneous? So in this point, we actually change it from being an equal sign here, where the delta G is equal, to working with an inequality, a less than, or that's part of an inequality equation. So they rearrange the formula, so you have the delta H minus T times delta S is when it's less than 0, so our G is less than 0, then that would be a spontaneous, the reaction would be spontaneous at that temperature. And we want to be solving for this variable for the T. So now we're going to plug in the values from the reaction to try to solve for T under those circumstances. So we have the negative 114.2 kilojoules per mole that was given, minus the T, times the minus 0.147 kilojoules per mole times Kelvin, and that's less than 0. So we want to solve for T. We're going to do that by adding 114.2 to both sides of this equation. Now we need to get the T alone, so we'll divide by this number here, which is what you have here. You have this over that, and the T ends up being, T is less than 777 Kelvin. So you're basically just solving for that variable T. All right, so here's another question on here. Actually, I think we'll go to the next slide. It says, what is the delta G for the following reaction at 297 Kelvin? Is it spontaneous? So this problem asks for the delta G of a reaction at 298 Kelvin. So we're going to remember this this formula here. If you can hear that bouncing around, that's my cat running around in the next room. All right, so anyway, we have to look at the products minus the reactants, okay? So in this case, we have the calcium chloride and the hydrogen gas. The hydrogen gas will be negligible because that's an elemental formation, and that's going to be 0. But we can look for the calcium chloride on this chart, which is here, and we have a negative 750 times the 1 because we have our imaginary 1 there. So that wraps it up for our product side, and now we will subtract for the reactants, which are up here, and the calcium is negligible because it would be 0 since that's in its elemental stage, and here we would look for the hydrochloric acid, which is here, the 131, and there's 2. You can see the stoichiometric coefficient, so it's 2 times the table value here, and then when everything is processed, we get a negative 490 kilojoules. Since this is less than 0, then the reaction is spontaneous. All right, let's look at 13.11. We're on page 480, and we have another question. It says, the delta H of a certain chemical reaction is 10.0 kilojoules, where its delta S is 123 joules per degrees Kelvin. So immediately I'm just noticing, right, that we have kilojoules here and joules here, so we're going to have to reconcile those. It says, this problem gives us delta H and delta S, and asks what temperature the reaction is spontaneous. All right, you want to see the noisy guy over here? That's this guy right there. In other words, it says they need to see for what temperatures delta G is negative. So we rearrange the formula, and just like we did in the last one, we have delta H is minus T over the delta S is less than 0. So first we convert the joules to kilojoules by dividing by 1,000. So we have 0.123 kilojoules over degrees Kelvin. Now we can plug it in to our equation up here, we have the 10 kilojoules for delta H minus the T, which we'll be solving for, times our adjusted kilojoules over Kelvin, the 0.123, and we have our inequality, it's less than 0. So in solving for T, first you can subtract the 10 kilojoules from both sides. It goes on the other side of the less than sign. But we have a negative T here. So when we multiply both sides in essence by a negative 0.123 kilojoules over Kelvin, then we have to flip this inequality sign. Here it's facing to the left, but because we're multiplying by a or dividing by a negative, actually in this case, the sign gets flipped to the right. So it goes from less than to greater than, and now our T is greater than 81.3 Kelvin. All right, so our last problem in this series is on your own 312. It asks the following question. Is the following synthesis of ethyl alcohol a spontaneous reaction at 298 Kelvin? And we have to calculate the delta G. So once again, we have the products minus the reactants. We'll start on this side, the product side. The way they set it up here, for some reason, they started the water first, and you have to look at the state. We have liquid, so liquid water here on the chart is negative 237. We have our imaginary 1 here, so it's 1 times that, plus it would, for the C2H6O2, we have that here. So it's minus 175 times our imaginary 1. That's our product side. This is all done here, the products. Now we have to go to the reactants. We start with the methane, the CH4. That is here, minus 50.8. There's a stoichiometric coefficient of 2, so we multiply 2 times that value. The oxygen is 0 because that's in its elemental state. And so the math works out to minus 3.1 times 10 to the second kilojoules. Since it's negative and it's less than 0, the reaction is spontaneous at 298 Kelvin. So that finishes the problems on page 13, on module 13, and I will be posting a separate video for the lab and for the study guide question answers.